Hello all and welcome to this third session of the course on pre-MBA statistics. So again, as you can see in front of you, so the title of the third session is going to be descriptive statistics. But again, before moving ahead and then before going through all the slides, I'll again as a habit quickly revise as to what we covered in the last couple of sessions. So again, if you vaguely remember, we've covered topics like, let's say, data types, where we talked about discrete data, continuous data, numerical data, categorical data, right? And the other important aspect that we covered already is sampling. So how exactly can you sample and what are the different ways of, let's say, sampling? When it comes to sampling, again, if you vaguely remember, we talked about ideas like random sampling, or which is also called a simple random sampling, stratified sampling, right? So again, the crux of the matter is, depending on the goal and depending on the data set you're handling, you should be able to pick a suitable sampling strategy and then collect the data. All right, and then once you collect the data, then we again talked about couple of ideas, right? So on one hand, you have descriptive, which will spend some time in this session and the next session. And once we cross the descriptive angle, then the idea is inferential. So again, if you vaguely remember, in the very beginning, the first session itself, we talked about these two schools of thought which kind of separate the idea of elementary statistics or rather empirical statistics. So once you collect the data, it can either go into descriptive stats or it can either go into inferential. Now again, what exactly do you mean by descriptive statistics? So descriptive statistics, which is again the heading of today's third session, is nothing but getting some insights from the data. So let's say getting some elementary measures, getting some summary variables, mean, median, mode, variance, standard deviation, skewness, kurtosis, maybe quartiles, maybe deciles, percentiles, right? So all these measures which I talked about right now fall under descriptive stats, or rather they talk about the shape or the behavior of the data set. And on top of that, along with all these measures, one can talk about all the graphs and all the plots and charts, etc. So again, like I said, we'll spend some time on handling descriptive stats, maybe again from a summary variable point of view and again from a graphical point of view, where one can actually have, let's say, a histogram or a pie chart, box plot, stem and leaf plot, okay, and so on and so forth. Okay, so the very first thing we'll talk about is, and of course the third session is going to be all about, let's say, some tables, graphs, charts, and how do you sort of structure the data and then try to analyze that. So now in front of you, what you see is a very typical kind of a table which is called as frequency table and the associated graphs. Okay, and this is a very standard, very typical kind of a data set that one should observe. If you pick any textbook, if you are collecting any practical data set, again, like I said, you have to fix the suitable sampling, collect a data set, and then this entire idea about descriptive statistics is the next step. So now here what you have is a small data set. So you have two columns. The first column tells you about starting salary. So the starting salary could be anywhere between, let's say, 47, 48, all the way up to 60. And again, you have a small description in the very beginning. So let me read that for you. So frequency table for a data set consisting of the starting yearly salaries. So all these are yearly salaries to the nearest $1,000. So when it says 47, it actually means $47,000, and these are starting yearly salaries of how many students or how many participants of 42 recently graduated students is given in the following table. So again, like I said, the data set is not very complex. You can kind of pause the video and then try to digest as to what the data set is telling you. But again, the data set consists of two columns. The first column consists of the starting salary. Now again, once you know the actual unit of the salary, then you can kind of spot as to what is the minimum salary, what is the maximum salary, and so on and so forth. So the starting salary start from 47,000 all the way up to 60,000. And more importantly, the second column tells you the corresponding frequency. So again, what exactly you mean by frequency? So frequency is nothing but the repetition each starting salary has. For example, the 47,000 salary is gone to, let's say, 4 students, or 4 students have a starting salary of $47,000. Similarly, then you have the frequencies to be 1, 3, 5, 8, 10, 0, all the way up to 1. So again, clearly, as you can see, the last 60,000 salary has gone to only a single recently graduated student. Okay. Now again, just by observing this sort of a frequency table, one can actually conclude a lot of things. Now when I say conclude, what exactly can you conclude? So here I can conclude a lot of things. For example, if you look at the earlier starting salaries, something like 47, 48 and the later part 57, 60. So 47, 48 is in the lower end of the spectrum, and similarly 57 and 60 is the higher end of the spectrum. So there the frequencies are kind of low, which also means that if you have like 42 recently graduated students from a particular location, particular college, something like that, then students getting either the lowest salaries or the highest salaries are kind of low in number. So here again the frequency, as you can see, are nothing but just 4, 1, 3 down the line, and then similarly at the higher end of the spectrum you have 3 and 1. And majority of the students are getting starting salaries which are lying here, which is denoted by, let's say, either 10 or 8 and stuff like that. So starting salaries in the range of, let's say, $51,000 or $52,000 are kind of the maximum. Okay. All right. So now the next idea is what exactly can you do using such a table, which is called a frequency table. So you have the number of observations on the left hand and the actual values of the observations on the left column, and the corresponding right column tells you all about the corresponding frequencies that each observation follows. Okay, so now the next thing is we'll talk about very elementary sort of graphs one can actually draw using the frequency table we saw in the last slide. So the first graph is called as a line graph, and again the idea is not very difficult. Again, if you sort of not follow the video and then maybe pause the video, try to digest the graph that you have in front of you, things would be rather easy. Okay. Now exactly what do you mean by line graph? So again the same data set that we saw earlier in the frequency table would be replicated using a line graph. Now again any graph should contain two axes, so x axis versus y axis. The x axis contains the starting salaries that you saw in the last table, so 47,000 all the way up to 60,000, and correspondingly the y axis simply plots the corresponding frequencies. So again if you vaguely remember the numbers from the last table, you can clearly see that the number of students having a starting salary of 47,000 were exactly 4. Similarly, let's say the number of students with a starting salary of 48,000 were exactly, let's say, 1, so 1 falls here in between 0 and 2, and so on and so forth. And down the line if you see that, again remember that number of students having a starting salary of $60,000 was exactly 1, and again in between if you remember that you had majority of the students, so let's say $51,000, $52,000, etc. So again number of students having a starting salary of $52,000 is nothing but 10. Okay. So what essentially you are doing is you are kind of plotting each starting salary and the corresponding frequencies using a vertical line, and hence the name of this very elementary or very starting sort of a graph is a line graph. Okay. And again what might be the advantage of such a graph is one can actually capture some trends, right? I mean, let's say beginning from, let's say, 47,000 all the way up to in the middle you have 52,000, you have an increasing trend. And again once you have the middle part of starting salaries 51,000, 52,000 exactly, then you have a downward trend, which also means again the exact same conclusion we talked about after seeing the frequency table is that majority of the students have a starting salary in the middle, whereas very few students have a starting salary at the lower end of the spectrum, and similarly very few students have a starting salary at the higher end of the spectrum. So I can sort of capture some trends, let's say upward trend, downward trend. At the same time I can talk about starting salary values where you do not have any frequency. So frequency value being 0, for example 53. So in the sample of 42 recently graduated students, you do not have any student whose starting salary is $53,000. Okay. And again so line graph is kind of a simple looking graph where you are plotting vertical lines corresponding to each starting salary and their frequencies, and you can spot trends, upward trends, downward trends. You can talk about frequencies which are empty such as 53,000. You can talk about frequencies which are low, for example 48,000 or 60,000 where you only have one student each, and so on and so forth. Okay. Now the next set of graphs would be just an extension of a line graph. So when I say extension, not exactly an extension, but we will go one step ahead. So maybe we will pour in some other information, we will maybe elongate the lines to make them like bars, and so on and so forth. Okay. So we will talk about a couple of other elementary rather standard graphs apart from a line graph. Alright, so now the next kind of a graph is called as a bar graph. Okay. So again the exact same data, the starting salary and the corresponding frequency data. The only difference is rather than a line graph I am talking about a bar graph. So now again an open question to all of you is, again maybe you can pause the video and try to answer that what exactly is the major difference between a bar graph and a line graph. So, can you try to answer this question? Alright, so hopefully the difference is, or rather answer to my question is not that difficult. So, a major difference between a bar graph and a line graph is that rather than having vertical lines corresponding to each starting salaries, I am having some sort of a bar. Okay. So, for example, again the exact same data. So, 47,000 you have 4 students, 48,000 you have a single student, 49,000 you have 3 students, 50,000 starting salary you have 5 students, and so on and so forth. And again down the line 60,000 starting salary you again have a single student. Now again you might think or you might wonder exactly as to what advantage a bar graph offers which a line graph does not offer. Okay. So again here the exact same conclusion I can draw, that I can see upward trends like this, I can see downward trends, right. I can see pretty much any frequency or rather any starting salary which is empty, for example 53,000, much more clearly than a line graph, because here you can see a hollow kind of a bar. Alright. So as opposed to a line graph where you did not have any lines, identifying a hollow bar is somewhat or rather slightly easier than identifying a hollow line. Okay. And on top of that I can sort of have an idea about where the area is sort of a maximum. So area means what? So where you have more number of observations. So for example, starting from 49,000 all the way up to let's say 52,000, in this area roughly I have more number of observations as compared to the later part. Okay. So again these are some of the slightly more advantageous features of a bar graph that probably a line graph cannot offer. So if you are only seeing let's say vertical lines as opposed to bars, then I might not be able to identify let's say hollow lines or somewhat like an area where you have more number of starting salaries or the frequency is more in that region, right. So see that these are some of the small advantages a bar graph offers as opposed to a line graph. Okay. So again my intuition or rather my point to all of you is rather digest all these graphs, see the differences that a line graph and a bar graph has to offer, see the advantages or the disadvantages of a bar graph as opposed to line graph and vice versa. Okay. So let's say for example upward trend, downward trend you can see clearly in both the graphs, right. Hollow frequencies, hollow starting salaries, hollow observations are much more or rather slightly more clearer or clearly observed in a bar graph as opposed to line graph. And thirdly what we discuss is that I can sort of identify a chunk where majority of the observations are lying slightly more clearly in a bar graph as opposed to a line graph. Okay. Now having said that, what might be a very big advantage of a line graph as opposed to a bar graph? So easy to draw or easy to sort of if you want to relay the information to some client or some other person, then it's slightly easier to explain a line graph rather than a bar graph. Okay, so now the third graph or rather third sort of a chart is called a frequency polygon. Okay. Now again exact same data, starting salaries on the x-axis, frequencies on the y-axis. Now again you may wonder that what exactly is the advantage a frequency polygon has to offer rather than a bar graph or a line graph. So again the idea here is that what we are doing is we are trying to connect the frequencies corresponding to the starting salaries and then drawing a polygon kind of a structure. So rather than having vertical lines individually or vertical bars individually and the starting salaries or individual observations, I am trying to sort of create a surface where observations are lying. So again how do you read a frequency polygon? Exactly similar to how we read a line graph or a bar graph. So again 47,000 starting salary of 4 students, then 48,000 starting salary of a single student, 49,000 starting salary you have 3 students, etc. The only difference is you try to identify those frequencies and try to connect the frequencies using a continuous sort of a line. And then ultimately what you get is a frequency polygon. So again this structure that you see is called as a frequency polygon. Alright. Now again talking about advantage of frequency polygon, one very elementary or rather important advantage of frequency polygon as opposed to let's say line graph or a bar graph is that I can directly identify area under the graph or rather area under the polygon and again clearly identify as to towards which side you have more frequency or you have more observations lying towards which side. Okay. So something like since this area seems to be quite large, then I can sort of tell very immediately that there would be more students where starting salaries are between 49,000 to let's say 52,000 or let's say 53,000. Okay, as opposed to the later half of the graph. So if you see this region particularly, then the area as opposed to this area is not that big. So I can kind of conclude that you don't have many students whose starting salaries are let's say more than 53,000. or similarly you don't have many students whose starting salaries are, let's say, less than 48,000. Okay. So, again the majority of the students having starting salaries between 49,000 to 53,000 are part of the data set. Okay. Now, again what might be a slight disadvantage of frequency polygon, again slightly difficult to sort of draw and relay the information from a frequency polygon as opposed to either line graph or a bar graph. Okay. So, here for example, I cannot individually tell the exact value corresponding to 49,000 starting salary, right. I mean, I have to sort of judge, I have to draw a vertical line here, something like that, and then again maybe retrace it back to the y axis to find the exact value of the frequency. So, since this entire polygon structure is a continuous structure, you do not have breaks anywhere in between, it is slightly harder to identify the individual frequencies corresponding to each starting salary value. Alright. So, these are some of the advantages of a frequency polygon and the cons of a frequency polygon as opposed to a line graph or a bar graph. Okay. So, now that we have talked about frequency, a frequency table, now the next kind of an important idea is that about relative frequency. So, what exactly you mean by relative frequency? So, again the idea is not very difficult to understand. So, earlier in the very first or rather the very beginning frequency table, what did you have? You had a starting salary column and you had the corresponding frequency column. Okay. And again the total number of observations on the sample size was 42, since the data set was sort of focusing on 42 recently graduated students. Okay. Now, what exactly to do is, in order to find out the relative frequency, I have to divide the corresponding individual frequencies by the sample size. So, again if you remember, the sample size n is nothing but 42, and again if you vaguely remember from the very beginning frequency table, the corresponding frequencies were these, right, 4, 1, 3, 5, 8, etc., all the way up to 1. Okay. So, in order to convert a frequency column to a relative frequency column, I am simply dividing the frequencies by n. Okay. So, for example, the first one would be 4 by 42, which is 0.0952, which you see here. Similarly, the next one will be 1 by 42, which is nothing but 0.0238, etc., etc. So, then 3 by 42, 5 by 42, all the way up to 1 by 42. So, again 1 by 42 would be exactly same as this, which is 0.0238. Okay. So, exactly what I am doing is I am converting a frequency column to a relative frequency column, and again you may wonder that what exactly is the advantage of a relative frequency column as opposed to a frequency column. So, couple of advantages really. A relative frequency column, if you again safely look at all these values, then all these values are somewhat like ratios or proportions, isn't it. So, all these values individually lie exactly between 0 and 1. Okay. So, if you compare a frequency as opposed to a relative frequency, frequencies do not lie between 0 and 1, whereas relative frequencies, all of them lie between 0 and 1. So, you can actually compare a value lying between 0 and 1. So, let me write down this way. So, relative frequency RF is always between 0 and 1. So, higher the value, or rather if the value is closer to 1, then you have more mass in that starting salary, or lower the value if the relative frequency is closer to 0, then again you can sort of conclude that you do not have many students having that starting salary. And essentially if you sum all the relative frequencies, so what should you get? So, again just repeat my question, if you add up all the relative frequencies, what should you get? So, sum of all the relative frequencies, summation RF is always equal to 1. Okay. So, essentially what you are doing is you are sort of dividing 1 in between all the observations you have. So, 47,000, 48,000, all the way up to 60,000, and you somewhat get proportions. So, again if you immediately see any relative frequency being above 0.5, you can immediately conclude that it contains a lot of mass, because 0.5 is the midpoint, or 0.5 is the half. So, if any relative frequency happens to be, let us say 0.6, 0.7, then you can immediately conclude that that corresponding starting salary has a lot of students in that. Okay. So, idea of relative frequency as opposed to frequency is nothing but their sort of proportions, and if you add all the RF values you should get 1, and they somewhat tell you the mass in relative terms as compared to all the other classes. And if you see any RF value being really close to 0 or really close to 1, you can sort of comment on the fact that it contains a lot of mass, or it does not contain that much of a mass. Okay, so now we can take another example, again just to sort of deviate from the starting salary and the 42 students example. So, this is a typical example which is kind of a slightly different example. So, the following data relates to disease type affecting 300 patients at a hospital. So, disease type affecting 300 patients at a hospital. So, again immediately I can sort of find out n. So, n is nothing but the sample size, which is 300. So, 300 is relatively much more than the earlier 42 which we had. Okay. And again this sort of a standard data set contains 3 columns. The first column contains type of disease. So, diabetes, hypertension, heart disease, asthma, stroke, kidney disease and liver disease. Now, the second column contains number of new cases. So, again you may pause the video and then sort of tell that this second column corresponds to what exactly which we have discussed so far. So, the second column which says number of new cases corresponds to frequency column, isn't it? So, 68, 75, 52, 40 etc. all the way up to 15. So, essentially what it means is that the number of people being affected by diabetes is 68. So, the corresponding frequency of diabetes is 68. Similarly, the number of people being affected by hypertension is 75, okay, etc. And lastly, the number of people being affected by liver disease is 15. Okay. Now, again like I said, just by observing the frequency column, I can talk about a lot of things about the data set. For example, can you spot the disease which is being affected to a lot of people, or can you spot the disease which is there in a lot of people? The answer is hypertension, because the frequency is on a higher side. As opposed to that, can you spot a disease which is not very prevalent in the people, which is liver disease, because frequency is on the lower side, which is 15. Okay. And then I can talk about a relative frequency column, which we just discussed in the last slide. So, what exactly you do is you take the frequency, for example 68, and then you simply divide by 300, okay, etc., etc. And then the next one for hypertension is 75, you divide 75 by 300. Then for heart disease you have 52, you divide 52 by 300, and so on and so forth. Okay. So, again if you see relative frequency wise, 0.25 is on the higher side, 0.25 is almost a quarter or exactly a quarter. So, you can say that among all the 300 patients at that hospital, exactly a quarter of the patients are suffering from hypertension, or 0.23. So, slightly lower than a quarter of a patients are suffering from diabetes, etc. And similarly towards the end, you can say that roughly 0.05 or just 5% of the patients are suffering from liver disease. So, liver disease, kidney disease, stroke, these are not very prevalent sort of diseases as opposed to something like hypertension, diabetes, heart disease, asthma. So, asthma is somewhere in between, so 13% and so on and so forth. Okay. So, a slightly different example where the sample size is on slightly a higher side. So, compared with 42 students, if you sort of extend the sample size to 300, then how can you conclude? Alright, so now a very important sort of a chart which I am very sure that almost all of you have seen somewhere in your lives and maybe in some textbook or some online resources here and there is a pie chart. Okay. So, now we will spend some time on understanding or rather analyzing how a pie chart is drawn, what conclusions can you sort of talk or rather gain from a pie chart and so on. Okay. Now, this pie chart corresponds to the exact same data we had on the last slide. So, disease data. Okay. And again you can clearly see that you have hypertension, diabetes, liver disease, kidney disease, stroke, asthma and heart disease. Okay. Now, how exactly should you construct a pie chart is you sort of create all these categories. By the way, the last sort of data corresponded to a categorical data because you have categories here, isn't it? So, as opposed to the earlier frequency table we had where you had starting salaries. So, starting salaries were all numbers, whereas this data focuses more on categories. So, diabetes, hypertension, heart disease are categorical data. So, corresponding to each category, how many people are being affected by that disease is given by the frequency column, and similarly the relative frequency. Okay. So, one very important idea is a pie chart is suitable when you have data set which is categorical data set. For example, the very last data set. Okay. Now, the only thing if you observe this pie chart for a second is you will gain information is that you sort of have all these categories and you simply plot the percentages or the relative frequencies in form of sectors. For example, 25% for hypertension, 23% for diabetes, 17% for heart disease, 13% for asthma and so on and so forth, and 9% for stroke, etc. Okay. So, the only thing I am doing is I am converting the earlier relative frequency column and I am sort of filling a circle or I am filling a pie with those many sectors or sectors having those many percentages. Now, some advantage of a pie chart. So, pie chart is a very standard sort of a chart which people sort of have in their presentations. They sort of put forward any data set for the clients, if they want to present the data, they want to put forward any analysis of the data, then they usually have a histogram, bar graph, pie chart, etc. Okay. So, for example, again from pie chart you can identify that liver disease is only 5% on the lower side, right. So, whichever sector corresponds to slightly more area, for example, hypertension, diabetes, etc., those are slightly more prevalent than all the other diseases. Okay. So, my suggestion is that play around with some data sets. So, go online, try to fetch some data sets which are categorical, they contain some frequencies, relative frequencies, and try to draw a pie chart by hand. Okay, so now the next idea is the idea of group data. So, what exactly mean by group data? So, group data in front of you, you can see a sort of a table giving lifetime in hours of 200 lamps. Okay. So, in this entire table, each and every value corresponds to item lifetime. So, lifetimes of, let us say, lamps, and then how many? 200 lamps. So, for example, 1067 hours, 919 hours, let us say 760 hours, 860 hours, etc. So, each and every lamp out of 200 lamps has a lifetime, right. So, lifetime means what? So, after how many hours would the lamp be defective? Okay. So, and then this is called as group data, and why exactly is called as group data we will see very soon. So, here what exactly we do is we can have some class intervals. Okay. So, again this table is nothing but a frequency table, but frequency table for a group data. Okay. So, again in the left column you see that you have class intervals. So, 500 to 600, 600 to 700, all the way up to 1400 to 1500, and similarly the second column gives you the corresponding frequencies. Okay. So, if you have the observations in terms of classes or in terms of groups, then the data set is called as a group data. Okay. So, again remember, if you go back one slide and then just gauge on the entire data set for a second, you will sort of find out that the minimum lifetime is somewhere in between 500 to 600, and similarly the maximum lifetime is somewhere in between 1400 to 1500 hours. Okay. So, once you identify the minimum and the maximum, I can somewhat divide the entire data set into equidistant classes or equidistant groups. So, again you may pause the video and then tell me that how much is the size of each class here. So, the size of each class here is 100, right. So, 500 to 600, 6 to 700, 7 to 800, etc. And then in order to generate the second frequency column, you have to simply go back to the earlier data set and try to identify that how many lifetimes fall in each class. For example, this 2 corresponds to nothing but there would be 2 lamps whose lifetimes fall in 500 to 600 hours, or there would be 58 lamps whose lifetime falls in 900 to 1000 hours, and so on. Okay. So, now in the next session we will spend some time on analyzing a frequency table corresponding to a group data, and we will talk about histogram, we will talk about couple of other plots, and so on and so forth. Okay. Thank you.